Welcome back to G Fun Facts Online. Today, we are going to dismantle a fundamental image you hold in your mind about our planet. When you imagine Earth from space, you almost certainly picture the blue marble. You see that distinct, hard-edged sphere of rock and water, wrapped in a fragile, razor-thin veil of blue atmosphere. We are taught in school that this atmosphere thins out as you go higher, effectively ending at the Kármán line, about 100 kilometers, or 62 miles, above sea level. Beyond that, we assume, is the black, empty vacuum of space. But that boundary is a lie. In reality, our planet is much larger, fuzzier, and more imposing than we ever realized. Earth is not a lonely marble in the dark. It is the heart of a colossal, glowing ghost. Surrounding our world is a massive cloud of hydrogen atoms that extends almost twice as far as the moon. This invisible, luminous envelope is called the Geocorona. And the most mind-bending fact about this structure is that for decades, we believed the moon orbited in the vacuum of deep space. We now know that when astronauts stood on the lunar surface in 1969 and 1972, they were technically still standing inside Earth's atmosphere. So let's dive deep into this invisible halo, explore the brand new images from late 2025 that finally revealed its true shape, and understand why this ghostly cloud might be the key to finding alien life elsewhere in the universe. To understand the Geocorona, we first need to redefine what we mean by atmosphere. Down here on the surface, the atmosphere is a thick fluid. It is a soup of nitrogen, oxygen, argon, and carbon dioxide, where molecules are constantly banging into one another. But as you go higher, the air gets thinner. Eventually, you reach a layer called the exosphere. The Geocorona is essentially the luminous, outermost part of this exosphere. It is a vast cloud composed primarily of neutral hydrogen atoms. Now, you cannot see this cloud with your eyes. If you were floating in the International Space Station looking out the window, you wouldn't see a glowing halo. That is because the hydrogen atoms emit a specific wavelength of ultraviolet light, known as Lyman alpha radiation. This light is produced when sunlight smashes into these hydrogen atoms, exciting them and causing them to scatter solar photons. Since Earth's lower atmosphere, the part we breathe, is excellent at absorbing ultraviolet light, the Geocorona is completely invisible from the ground. It can only be observed from space, and even then, you'll need specialized instruments to see it. But it is there. It is a tenuous, glowing fog that envelops everything in Earth's immediate neighborhood. While this might sound like theoretical physics, our understanding of this phenomenon has just undergone a massive revolution. As of late 2025, we have moved from grainy archival data to high-definition reality. This is thanks to the recent success of NASA's Carruthers Geocorona Observatory. This mission, formerly known as GLIDE, was launched in September 2025 with a singular purpose: to image Earth's exosphere from a vantage point nearly 1 million miles away. The observatory sits at the gravitational balance point, known as Lagrange Point 1, situated between the Earth and the Sun. Just recently, in November 2025, the observatory sent back its first light images, and they are breathtaking. These ultraviolet portraits reveal Earth not as a hard-edged rock, but as the bright nucleus of a fuzzy, glowing sphere. For the first time in history, we can see the full extent of our hydrogen halo breathing and shifting in real time. We can watch it respond to solar storms and the pressure of the solar wind. These images have confirmed what scientists had long suspected, but could never fully visualize: that the Geocorona is a dynamic, living extension of our planet. However, the story of how we discovered this invisible structure is a detective story that spans half a century, and it is filled with missed clues and ironic twists. The first photographic evidence of the Geocorona was actually captured by a human hand. We have to go back to April 1972, during the Apollo 16 mission. Astronauts John Young and Charles Duke set up a small, gold-plated telescope on the lunar surface. This instrument was the Far Ultraviolet Camera Spectrograph, and it was designed by the visionary physicist Dr. George Carruthers, the very man for whom the 2025 observatory is named. From their vantage point on the moon, the astronauts pointed the camera back toward Earth. The resulting image was ghostly and beautiful. It showed Earth surrounded by a bright, diffuse glow of ultraviolet light. It looked like a nebulous ring, but here's the irony. At the time, the astronauts and the scientists back home believed they were looking at the Geocorona from the outside. They assumed this hydrogen cloud ended somewhere between Earth and the moon. They had absolutely no idea that as they stood there on the lunar soil, adjusting the camera, they were standing right in the middle of the very atmosphere they were photographing. The true scale of the Geocorona remained hidden in archival data for decades. It wasn't until 2019 that a team of researchers, led by Igor Balyukhin of Russia's Space Research Institute, made a startling discovery. They were digging through old data from the Solar and Heliospheric Observatory, or SOHO. SOHO is a joint mission by the European Space Agency and NASA that launched way back in 1995. It carries an instrument called SWAN, which stands for Solar Wind Anisorsophies. SWAN was designed to map hydrogen across the entire solar system, looking for the boundaries of the heliosphere. But because SOHO orbits near Earth, SWAN inadvertently captured detailed data of Earth's immediate neighborhood. When the researchers analyzed this ignored data, they found that the hydrogen signal from Earth didn't fade away as quickly as the old models predicted. They traced the Lyman alpha glow outwards and realized the Geocorona extends out to a staggering 630,000 kilometers or 391,000 miles from Earth. Now, consider this. The Moon orbits at an average distance of about 384,000 kilometers. This means the Moon is deeply, undeniably embedded within Earth's atmosphere. We orbit inside the ghost. So how does an atmosphere stretch that far? What are the physics that allow Earth to hold onto gas atoms nearly 400,000 miles away? It all starts with water and methane. The hydrogen in the Geocorona ultimately comes from water vapor and methane near Earth's surface. As these molecules rise into the upper atmosphere, they are bombarded by harsh sunlight. This triggers a process called photodissociation, which breaks the molecules apart and releases individual hydrogen atoms. Because hydrogen is the lightest element in the universe, these atoms float to the very top of the atmosphere. When they reach the exobase, which is the bottom of the exosphere, roughly 500 to 1,000 kilometers up, the physics change. The air becomes so thin that atoms stop behaving like a fluid. They don't bump into each other and flow like wind. Instead, they launch like tiny cannonballs. This is what we call ballistic trajectories. Some of these atoms don't have enough speed, and they fall back toward Earth. But others have enough energy to soar hundreds of thousands of kilometers into space before gravity slowly pulls them back. A small fraction even reaches escape velocity and is lost to the solar wind forever. This creates a cloud that is not a perfect sphere. It is sculpted by the sun. On the day side of Earth, the pressure of sunlight literally pushes against the hydrogen atoms, squashing the Geocorona. On the sunward side, it extends roughly 60,000 kilometers. But on the night side, facing away from the sun, that pressure is released. The Geocorona stretches out into a massive, long, comet-like tail. This is the region that engulfs the Moon. Now, I want to be clear about what we mean by atmosphere here. Despite its immense size, the Geocorona is incredibly tenuous. We call it an atmosphere, but it is thinner than the best vacuum we can create in a laboratory on Earth. At 60,000 kilometers out, the density is only about 70 atoms per cc. Out by the Moon, it drops to just 0.2 atoms per cc. For comparison, the air you are breathing right now contains about 10 quintillion molecules per cc. So while the Moon is inside the atmosphere, there is no wind, no air pressure, and certainly no breathability. It is a vacuum, but it is a vacuum filled with the faint, telltale signature of our home world. Why does this matter? Why should we care about a cloud of hydrogen so thin it's essentially nothing? The existence of the Geocorona has profound implications for astronomy, space travel, and the search for alien life. First, for astronomers, the Geocorona is actually a massive nuisance. Space telescopes like Hubble or the James Webb Space Telescope often want to observe the ultraviolet universe to study the formation of distant stars and galaxies. However, because these telescopes orbit relatively close to Earth, they are constantly looking through this fog of glowing hydrogen. This background noise acts like light pollution. Just as city lights make it hard to see faint stars, the Geocorona's Lyman alpha glow can drown out faint UV signals from the early universe. The recent realization that the Geocorona extends past the Moon means that even if we built a telescope on the lunar surface, it would not be free from this interference. To truly escape Earth's halo, a UV telescope would need to be sent deep into interplanetary space, far beyond the reach of our planet's exosphere. But perhaps the most exciting application of Geocorona research lies in the hunt for exoplanets. As I mentioned, Earth's hydrogen halo is a byproduct of water vapor breaking down in the lower atmosphere. This means that a Geocorona is a potential biosignature, or at least a water signature. If we point our telescopes at a rocky exoplanet light years away, and we see a similar hydrogen Geocorona surrounding it, it could be a smoking gun for the presence of water oceans on its surface. Astronomers are already using this technique. When a planet passes in front of its star, known as a transit, we can look for the absorption of Lyman alpha light. If we see a massive cloud of hydrogen bleeding off the planet, it tells us the planet is losing its atmosphere and likely has water vapor to spare. Understanding the shape, density, and behavior of our own Geocorona gives us the ground truth we need to interpret those signals from alien worlds. We are essentially using Earth as the control group for the rest of the galaxy. Finally, the Geocorona acts as a visible monitor for space weather. When a solar storm or coronal mass ejection hits Earth, it compresses the magnetosphere and energizes the exosphere. The Carruthers Observatory is now allowing us to watch this happen in real time. By observing how the Geocorona brightens and shifts during a solar storm, scientists can better predict how these storms will affect satellites, GPS systems, and power grids on Earth. It gives us a visual warning system on a planetary scale. The discovery and visualization of the Geocorona challenge our fundamental perception of Earth. We are conditioned to think of boundaries. We think of borders on maps, the shoreline of the ocean, or the edge of the atmosphere. But nature rarely deals in hard lines. The Earth does not end at the ground, nor at the clouds, nor even at the Kármán line. It fades. It feathers out into the cosmos, creating a bridge of hydrogen that links us to our satellite and the solar wind beyond. When you look up at the moon tonight, remember that you are not looking across empty space. You are looking through the outer reaches of our own home. You are looking through the Geocorona, Earth's invisible, protective, and ever-expanding halo. Thank you for listening to G Fun Facts Online, and keep wondering.